Hi, so the topic of today's lecture is, we're starting with machine learning with neural networks, but we'll talk mostly about representation learning or feature learning immediately after we kind of cover the neural network models. So let's move on. Why neural networks for music? So first of all, it's not a new research direction. Already in 1991, there was a compilation, a book that came by Peter Todd and Garrett Loy, Music and Connectionism. That was the common term then for neural networks. But today, I mean, there was so much development, so many new things that came up with using neural networks, especially the deep learning, that this renewed interest also spills to music, of course, and not just spills, but it actually provides some very interesting and important results. So broadly speaking, yes, I mean, neural networks are just machine learning techniques, but they have their own specific way of framing the machine learning problems. So with the technical advances today of the optimization algorithms, the availability of a lot of data, and the computing power, we can actually see some amazing results. So let's talk about neural networks in general a little bit. Oh, maybe before that, the main applications for music, right? So of course there is the music information retrieval field with the conferences and publications. As any information retrieval, basically deals with the ability to search and find content by some queries that might be quite elaborate in the sense of terms like genre or style, and the examples we have seen on Friday kind of attest to this type of research. And this course, at least from my own personal interest in research, I'm kind of gearing this more towards generative modeling. But one thing that neural networks allow to do is really focus on finding efficient representations. So feature learning or representation learning is really something that I think has become a very important aspect of deep learning today. And this was always a difficult question for music. So we devoted a lot of time to talking about representation, the data structure. I mean, how the data is structured, how it can be analyzed by human engineered features or some mathematical transformations. So there is kind of a interesting and important borderline between how much of our knowledge and human engineering we want to put into preparing the data, and then how much we can actually let the network build its own internal structures that capture things that maybe we could not have thought about by doing this manually. Now, representation learning is a specific field in machine learning, although there are conferences devoted to machine learning for representation. Specifically to music, I think this task is important because unlike other domains where you might want to look for specific things that the theory explains already, like concepts like phonemes or lexicons and words and language structures and grammars in natural language. In music, so-called semantics, well, syntax semantics, I mean, here we use the words really just for their very broad understanding. But, the rules of composing music, how it's structured, and then the meaning of music are really hard to define. So unlike other domains where we might want to build things knowing that there are certain categories that we want to detect, in music it's very hard. Even things like emotions that many people talk about. One of the meanings of music is emotions. Unlike text, where you can say sentiment analysis could be kind of correlated to positive and negative words, we can say that maybe some scales are more happy, some scales are more sad, but really this is a very broad and very ambiguous and dubious characteristics. I mean, what is the emotion of music? What is the meaning of music? So music theory people try to define meaning of music in different contexts. Some of this is really just self-referential. By repetition, you create meaning. Some are talking about expectations and anticipations, and this is where a little bit of that information dynamics approach falls, trying to see how predictable music is and how surprise is related to the musical emotions. And there is a lot of research on music anticipations. For those interested, there is a book by David Huron called Sweet Anticipation that is only devoted to trying to explain music as expectations and violations from expectations. But in general, these are all kind of very vague terms. So if the neural network can build something that we can handle, and maybe we can understand what the internal structure is, but in any case, it could be a very useful tool to work with. The other problem about representation learning is that because music has so much variability, so many genres, so many cultures, you can also talk about idiomatic or personal style. So if a certain musician tends to improvise with certain licks, it's going to be very hard to kind of get someone to theorize about this in a general context and say, well, these are the meaningful units, or this is how this music is analyzed. People do try to do this, of course. There are theories about bricks and licks, and but if we can let the network figure it out without spending too much of our own brain power, and maybe do this automatically. I mean, we kind of mentioned the idea that these networks, one of their applications is really allowing to improvise and possibly do this in different styles. So I'll bring one example of generative modeling, which kind of combines the idea of a certain representation that is learned by a network without us really knowing what the representation is, and then how it's being used to improvise. I mean, this example actually will carry over to also tomorrow's class, where we start talking about variational autoencoders, and then later on recurrent neural networks. The Piano Genie is a project by Chris Donahoe, who was our PhD student, and now he's doing a postdoc in Stanford. And this is a project he did when he did an internship in Magenta, Blue Magenta. So the idea was that we want to have some low-dimensional control over a piano. Now, some important points again to take from this example, even though we're not going to talk specifically about RNNs, we're going to talk about autoencoders and PCA in the second half of this class. But the concept itself, that there is some kind of an internal bottleneck, internal representation that compresses the knowledge in some efficient way. And then by generating more example, by triggering the internal representation in either totally random ways or maybe less random ways, and this is what Chris will be doing with this 8-button controller, you can then decode or reconstruct the structure. So since we have seen already the concepts of encoding, decoding, when we spoke about information theory, I think this is a good way to think about this. I mean, the fact that even the terminology is used as encoder, decoder kind of has a reference to the idea that we find in the presentation of a data that is in some sense an encoding, and then we decode it. And since we mentioned also lossy representation, this is definitely a lossy representation. So what this project is about. So Chris trained an and we mentioned RNN on Friday. So Ross was showing some examples of RNNs and CNNs. So this is a sequence-to-sequence RNN, where you have a sequence of nodes that go through this internal neural network structure that has these time links and also mappings to the outputs. And then in the sequence-to-sequence, you basically try to decode it. And when you decode it, in this case, and this is something that is going to be common to what we're going to do today, which is an autoencoder, we want basically reconstruction of the same input. Now, the only difference is going to be that here we have also time links between the states, while what we'll do today is much simpler. We just map this to some internal representation and directly reconstruct. So we'll show a simpler case as a start, and then we'll talk about RNN in a couple of classes. So, so that's kind of the whole setting. You take a big corpus of musical pieces, and then you kind of map this to these, well, here it's only 4 on the graph. In the video, there are 8. There are some questions. How would you map it in a way that will be meaningful? Then if you trigger them in certain ways, that it will be mapped to a more meaningful generations. But we will not go right now into that paper specifically that suggests a specific way of encoding that will have this usability criteria. Basically, that let's say if you trigger states in some kind of descending or ascending way, that it will map to same gestures on the keyboard. This is kind of an additional aspect of how you kind of design your architecture, which is specific to this project. But like in a larger context, I mean, what's important is that, of course, we don't know what these latent states are. So if you really want to use them, you need to put some extra effort to trying to understand what they are, or kind of try to add some design considerations. So you would know that some manipulations here will translate to kind of corresponding intuitive changes in the output. And this is what we'll see here right now. So let me play the example, and so we kind of get an idea of what the network does. And just to repeat again, I mean, it's lossy because what we'll be triggering is from 4 or 8 buttons. We'll be triggering a full grand piano keyboard piece, and the triggers are basically learned from encoding, decoding a specific corpus. So this is music in a very specific style. You can also check out the link, and it has a web application and a link to the paper and the repo. So here is an example of that improvisation. I think you got the idea that this system allows us to be creative from very small subset of inputs, and then of course there's a question, well, what are the applications, and I'm sure you can come up with some great original ideas. Of course, the intuitive one would be that somebody could compose music by specifying something without really having to know rules of harmony and melody. Of course, the control is not perfect, but it could be sort of a fun toy. If you can constrain this to a specific sequence of chords, or add another constraint of a structure, you can actually get a lot of mileage out of this idea. So moving on to talking about neural networks, we mentioned the simplest or the first type of fully connected neural network that introduces just the concepts of so-called backpropagation as a way to learn the weights. And the popularity of this approach, where we basically specify a problem by giving input and output and a loss function and the optimization algorithm, became a paradigm in programming. Some people already call this today differentiable programming, which emerges from so-called libraries for auto-differentiation. So if you're able to write a program, so instead of thinking about logic and loops and if and then clauses, if you're able to define your problem as some kind of a mapping between input and output with a cost function, then you basically your programming is actually building this architecture, specifying these aspects, and then the program actually learns or optimizes itself to create this mapping from input to output. And why it's programming? Because eventually you do create an input-output relation. So like any function, you have some kind of arguments in the input, and you have some output that the network generates. But instead of you writing the logic, you just specify the terms according to which the differential programming will operate. So the elements, and I'm kind of a little bit repeating the materials from Friday, from Thursday, sorry, from the last class on Thursday. We have these neurons, which are motivated by, the biological neurons. Each one basically sends a signal, fires, and the next neuron integrates all the inputs. And this is done by basically specifying this integration function here. So each X, when it fires, it has a weight W. It's all integrated or summed on each neuron here. Each neuron has its own bias, basically. So it can kind of shift its, if this is zero, kind of around zero, you can shift the weight by some bias B, which is also parameters. You can think about this, just put constant input with the weight B. And now all of this is translated into a number between 0 and 1. So this activation, this sigmoid, is actually as shown here. This is the same equation, and it plugs in this number. So Z is this expression in the parentheses, and because this expression can go from minus infinity to plus infinity, what the sigmoid does, it translates this to a number between 0 and 1. We'll talk later about linear neurons, or neurons that don't have the activation function. In this case, we just don't have the whole, 1 divided 1 plus x, and we only have the z. We only have this activation here, and we'll see why these activations or the nonlinear activations are important. But anyway, if this is the basic computing element that we have, we also need to find some kind of a cost function of the output. You have seen this already. And in this case, if we take some kind of a square error, Euclidean distance, if you want, and we sum over all possible inputs, and you have the desired outputs, we kind of average all of this, and we get the cost of approximating the desired A with outputs of the network. So y of x is the output, y given an input x. So the whole idea of auto-differentiation or backpropagation is that now we can change the weights, so our output becomes closer to what is desired. So by making a small change in the output, we basically differentiate this function, and the small change in the output will be changing the output by changing the weights, and the weights are the W's and the B's, and this is basically a chain rule in calculus. that is applied to backpropagate the error. Of course, we are not showing and proving the full backpropagation method and algorithm, but the concept itself is that once we have the ability to change, we want to be able to change the cost function so we reduce it. Let me, I'll connect myself to Ethernet instead of Wi-Fi, sorry. Okay, I hope it will be, I had my internet signaling some problems. So if we go back to the idea that we have a cost function that we want to optimize, this graph shows a hypothetical cost function, which is very nice. It's kind of like has a single minima, and if we are in and these, the V1 and V2 would be the parameters of our network. So if we are able now, and of course, as we have seen also in the Keras examples, you have thousands of these parameters, but this is just for the visualization. Assume you have 2 parameters that you can optimize. So, so the whole idea is that if you change these parameters, you will change, of course, the cost function, or in this case, how well your network approximates some desired mapping or value. And what we want to accomplish is actually to go and slowly change the weights until we hit the optimum or the minimal cost. So what we do, we use gradient descent to find the weights and biases that minimize the cost function. And this is done, so the change in the cost function will be done by looking at the gradient. So this upside triangle is the gradient, the derivative of C in multiple dimensions. So if we take this direction, okay, and we change each V by some delta, okay, we'll be actually moving down this slope. Now, this is something that was already explored by biology motivated early neural network people called Hebb rule. And the idea was that neurons actually, the biological neuron, kind of have this adaptation that could be described as Hebb rule, because indeed in biology, neurons that tend to fire a lot together, and so there is this kind of 2 types of connections. One is that actually encourages or facilitates the synapses become more sensitive, and other are inhibitory. So there is kind of a change in the sensitivity of each neuron to other neurons that it's connected to, which here mathematically is represented by changing the weights. So if there is a change in the weights, okay, given that there is some kind of a cost function that navigates this whole process, by plugging this in, okay, we can see that if we go with a step eta, this is the step and this is the direction. So if we plug this in here, what we get is basically this equation. So actually the arrow should go like this way. So this is the change. So given the Hebb rule, we basically see that the change is proportional to the square of that gradient with some step, and this is our learning rate. And the way we actually update the weights, we take the previous weight and we update this by this delta. So written now back in the notation of the previous slide, we have exactly the same kind of thing. We have the V's becoming the weights and the biases, and we update this every step with this gradient calculation. Cost functions. If we use a quadratic cost function, we can basically calculate on either mini batch on some subset of M steps and update. And that update will be basically each one of these errors, and each one of these errors will be basically just the derivative. So it will be 2 times, and we can divide by 2 times the difference between Y and A. Another function that is important, and we'll talk about this a little bit more at length, is the cross entropy. Cross entropy very often is used with categorical variables. So in that case, we might want to have the output as being a probability of some categorical answer. So we have a binary variable. We might have basically the probability of, we want y to be either 1 or 0, and a would be the probability of that answer. So it resembles cross entropy, and we'll see in a second why, because if you think about them both as probabilities, this is like an entropy expression, just that here you have one entropy, one P, and here is another Q. We'll talk about this example later, but just for now, just keep the idea or the name of cross entropy as this cost function. So does any function work? So if you want to check about autograd and autodiff and see how they operate, and can you define any function that will create the back propagation rules for you to optimize. So not every function, of course, works, and there are not differential functions. There are things that we cannot propagate back, and we'll talk about this also once we talk about variation autoencoders. If we have some kind of probabilistic element in the middle, we have to come up with some tricks that will allow back propagation to work. But for now, let's stay with these two main functions. So the whole idea of gradient descent-based machine learning or this differential programming is that you define a neural network with some parameters, you choose a cost function, you optimize the cost function. To do this, you need to be able to calculate the gradient of that cost function as a function of the parameters, and you have the neural network frameworks that can do this for you. Now, one other element to mention is how do we encode our musical data for the neural network. So a very common encoding is one-hot encoding. So at least in case of like musical notes, so here we have an example of 12 notes. If we have only one note present every time for a melody or monophonic representation, you can basically trivially encode this as 1, meaning that the note is present, and 0s if this note is absent. But if we have polyphonic music or music that has multiple voices, we will have several notes active together. That becomes a little bit of an issue, because then we wouldn't know exactly at the output of that network which notes to choose. And we'll talk about this in a second, because the network actually doesn't operate with 0s and 1s, it operates with probabilities. So even if we encode input like that, and then we decode it, we want to decode the output into something like that. In this case, we can always choose the maximum, and this will be, the straightforward way to do this. And I think there were also questions on Piazza about Markov model. What do you do if you always choose the maximum probability? You might be stuck in the loop, but you basically can have multiple probabilities here. So how would you choose which one? So we'll talk about softmax. But if we have many hot encodings, which means we actually allow many nodes to be present, how we would know where to put, how to cut our outputs, because all of these will be probabilities. And then do these probabilities average into like one number, because we have certain chords that can appear in certain configurations, or do we expand this in some kind of a hot alphabet over all possible combinations. There is also this notion of so-called multi-one hot, which you can have basically several one-hot representations for each of these nodes, or multi-many hot. All of this is pretty important once you start designing the network, because it immediately not only reflects on the architecture of the network and the complexity of the network, but also the more parameters you have to learn, the longer it might take you to train, and so on. So let me kind of just emphasize that this point of what happens when we have multiple outputs at the end, right? So with a single neuron, we said that we have this activation function where we can think about Z, okay, as the overall activation between -infinity to infinity that the neuron spits out. And then we want to translate this to a probability. So if all we have is one neuron at the output, and we want it to fire or not to fire, or if we have a binary classification problem, we want to know if this belongs to class 1 or 2, we can just use the single neuron probability. And again, this is, sorry, that's the wrong graph. This is the logic. That's the inverse of this function. I'll correct this in the slides and repost them. But the idea is that this will translate, yeah, this is the correct graph here. This is the sigmoid function. This translates numbers between minus infinity to infinity to numbers between 0 and 1. Now, if we have multiple neurons, then the question is, what is the probability? Let's say you have C outputs, and then the question is, given the activation of all the neurons, what is the probability of each one of these classes to be active? So one way to generalize this is basically have this kind of expression. We still have e to the power of z at the top, and we normalize them by all of the sum of EZs. If you want, you can also multiply this by EZ. You'll get here an EZ, and here get EZ plus 1. And you can think about this as normalization, this e to the power of z. So they're kind of, this is generalization of this representation. So what we have here is basically some numbers here, okay, which will go, if z is infinite, it'll go to infinity. If z is minus infinity, it'll go to 0. And then you normalize, you divide this by total number of these activations, so you'll get something between 0 and 1. An important extra parameter that we will encounter possibly when we talk about RNNs, but also for other networks, this parameter was introduced, and this is something that divides the z by some scale factor. So the canonical, this will be called softmax. The canonical one has just the z's, but you can weight them by some number. So if we weight this number, it's if you use the temperature, divide this by temperature. And the idea is that now we have this kind of a way to reconsider how we go from, let's say, temperature 1, which was the original distribution. So if we have these probabilities over different classes or different outputs, we can then, by basically decreasing the temperature, we kind of emphasize the strong elements. You can kind of like work out the math here. I think intuitively it kind of explains why whatever, you know, the lower T gives more emphasis to the bigger Z's. So whichever, so this Z, which is slightly bigger than this one, the more we lower the temperature, you can see that the relative weight of these two stronger bins becomes higher compared to the rest, and then they kind of like start being more prominent. And of course, at a certain point, these start competing between themselves, and then you would select the strongest one. So why do we introduce temperature? For several reasons, and we'll talk about this in the next graph, but you can think about this as a way to decide basically how much or how to select from your probabilities. So let's say you created a neural network and now you have outputs, and these outputs are given some z's, and these z's with t equal 1 give you this kind of a histogram or multinomial distribution. So what does that mean? Think about this as the output layer of your neural network that has multiple classes at the output. So these could be nodes, these could be words. So this is the distribution over the next word. Very much like in the Markov model. If these are states, this is the probability of you now to choose the next state, okay? So you can, you know, throw a dice basically, or use a multinomial distribution function and select based on this vector of probabilities with the relative weights like this, okay? On the other hand, you know, we can always say, let's go for the maximum one, and maximum will be this one. You can say, well, let's try to go maximum and then maybe give more preference to this one, but we don't really want to go on the low probability bins. So how would we consider all of these options between going on the maximal probability or just a multinomial where we just randomly choose according to these weights? So this is kind of an elegant way to kind of give this solution. You can always use kind of a multinomial distribution, but by changing the parameter t, you go between selecting the maximum to selecting between the the most prominent or strongest probabilities to the idea that you can select all of them. It also works the other way around. Like if you keep now increasing the temperature, so temperature could go to 2, 3, and so on, you eventually will flatten this out and you'll have totally equal probability over all possible outcomes or all the states. So it kind of gives you this additional knob to control your outputs between being equal distributed to being more biased towards the strong probabilities. Just optional, I included in the slides the derivations of the learning, and so I will not go through this the math. You can check it yourself, but I'll just kind of explain why I put it here. So this is our cross entropy loss function. As you see, it's the target times the output log yc. You can also think about this as basically kind of weighted. If this is probability, so this is the probability times how many times TC shows up in our categories, in our examples. But this is the function that we are trying to optimize. If we now do the differentiations of y by z, okay, the activations, if you follow these equations, you'll see that we have these two aspects, dy over dzi or dyi over dzj, okay, and the activation of neuron, so activation of neuron I influences the output at y according to this equation. So you have to kind of, it's a very neat expression, but of course you need to go through derivation and show that this is true. So this is actually a probability that y will happen times the probability that it will not happen. And also, if you have an activation on neuron J, it also affects the probability at output Y because we kind of sum them all together. So this idea that you have to normalize with this sum here, which is the sum here, the idea that you normalize that neuron J also enters into the normalization of I, so it also appears there. So yeah, that's kind of another point to consider, that you, in this derivative, you have this relation yi, yj. So this is how they're correlated. And then if we use these two equations, we plug this into the derivative of this, we come up with this learning algorithm. Why it's interesting? Because basically what it tells you is that it tries to bring the y's, the outputs, close to the target. Okay, and if y is bigger than t, you'll have a positive change. If y is smaller than t, you'll have negative change. But this is how you would update. This is what will be the update parameter, and of course you will scale this, then multiply and use this rule here. So what we're calculating is only this kind of a change of the gradient in the cost function, and then you apply this weight to update your neurons. Now, the effect of temperature can be also kind of considered in this context. So if we have now two targets, we have a target which is expressed not as a categorical variable with ones and zeros, but as a probability and weighted this way, we can actually learn the Q's and the P's. So our targets are the P's, Q's, what we learn. So basically I'm using this expression here. So if this is our new learning function, it will have also 1 over t here, and kind of, this is, if you want to check out the math or a little bit more detail, this is from this paper by Hinton. And why I'm bringing this up. So if you run through all these derivations, you can see that for high temperature, we can approximate this expression with the Taylor approximation. Then we can assume that the sums of Zi's and sums of Vi are 0. So you can write the algebra, you get to this point. So at high temperatures, the temperatures that are relatively high to the activation levels of Z and V, the cross entropy update rule becomes same as minimizing an Euclidean distance. You can see, because if you do a derivative on this, you'll also get Zi minus Vi. So it kind of gives you also this soft way of going between Euclidean error to the cross entropy, which is logistic regression or classification, where we actually think about variables as categorical versus as a continuous variable. So that's kind of another thing to consider. And at low temperature, basically, the learning is more categorical, so it pays attention to more likely firing neurons or Z that is bigger than for the strong Z's. This proposal actually came in the context of so-called distilling knowledge, where the idea was that learning from categorical or labeled data where things appear, there is like a true and false answer. It might work if you have very elaborate networks that can actually, or ensemble of networks that can actually learn the concepts very, with a lot of parameters and, what he calls a cumbersome network. But by introducing the temperature, it kind of allows you also to consider now the errors, the low probability, because what his idea, the claim was that you can take a very big network and it will learn concepts, but now you might want to have a small network that kind of replicates the knowledge of the big network. Now that small network will not be able to learn from the data itself, but it might be able to learn from the softmax decisions of the big network. So by providing the small network with also probability instead of categorical variables, which basically means learning with the temperature, will allow smaller networks to actually learn something that otherwise would require huge networks. So this is pretty much the overview of neural networks and how they're being trained, very much just providing the math and repeating Russell's lecture on Thursday. So I'll stop right now and then we'll move on to talk about the next step, which is the autoencoder. Yeah, so that's our next topic. Sorry. Yeah, let me pause right now.